Hi and welcome to our project presentation. My name is Kristoffer Flemström and my colleague is Linus Johansson. Our project was to design a ventilation solution for a metal mine. The project is part of the Kurs utvecklingsprojekt K7006B at Luleå tekniska universitet. The group is introduced to the project in the middle of it, because an employee has left the project. The employee that has left is sick, so he can't do a proper handover. But he have done a basic mine model in Vensim and determined how much equipment is needed in all parts of the mine. The mine is planned to be constructed in two parts. The smaller part is called Juno and the larger part is called Jupiter. The two parts is connected to each other by a transport ramp. All necessary air for both parts of the mine is sucked in by the access ramp in Juno. The airflow after that split off. The split off occurs in the junction between Juno's ramp and the access ramp to Jupiter. Because this mine is a shallow mine, the air is calculated to be incompressible. The necessary airflow is mainly influenced by the machinery that operates in a specific part of the mine, where the engine power is used to calculate the needed airflow so the exhaust isn't harmful for the workers. The equation takes the total engine power in the part of the mine and multiply it by 0.05 cubic meters per kilowatt. And the 0.05 is according to health and safety regulations. This leads to an airflow in Juno to be 78 cubic meters per second and in Jupiter 116 cubic meters per second. Air losses in Juno are estimated to be 20%. And in Jupiter to be 40% by our prior co-worker. This leads to a required airflow of 94 cubic meters in Juno and 162 cubic meters in Jupiter. When we know the required airflow in both parts, we can calculate the optimal exhaust shaft diameter. To do that, we need to take 8 things in consideration, 4 known and 4 unknown. The 4 known are establishing cost, shaft length, annual interest, operational length of mine. The 4 unknown are annual cost, excavation cost, shaft diameter and total cost. Annual cost is taken directly from Vensim. To get the annual cost, some alteration in Vensim settings is needed. The power cost is changed to 0.2 Australian dollar per kilowatt. The fan efficiency is reduced from 80% to 70%, and the mine's operational lifetime is set for each part of the mine. Excavation costs come from this chart, where you test all diameters in an Excel chart. You take one diameter to see how much it will cost to dig out one circle section with that diameter, 1 meter deep. Then you multiply the given number with the shaft length and add the establishing cost to get the excavation cost. To get the total excavation cost for each diameter, we use this formula shown in the picture. For Juno, the optimal diameter is 3 meter and the cost is 423,446 Australian dollar. For Jupiter, the optimal diameter is 5 meter at a cost of 2,023,820 Australian dollar. In Juno, this gives a fan duty point where the flow is 94 cubic meter per second and a pressure of 12.1 Pascal. In Jupiter, this gives a fan duty point of an airflow of 162 cubic meters per second and a pressure of 408.6 Pascal. The ducts hang 30 centimeters from the roof and need a security distance between the LHD and the underbelly of the duct to be also 30 centimeters. This gives a total of 0.6 meters of spacing. In Juno, the ore passes are 4 meters high, 3.4 meters wide. When the spacing is accounted for, the remaining height is 3.4 meters. Satisfying airflow is reached when 1 meter duct is used. This gives a maximum height of 2.4 meters for machinery. The best fit were Sandvik's LH410. In Jupiter, the ore passes is 4.5 meters high and 4.5 meters wide. When the spacing is accounted for, the remaining height is 3.9 meters. Satisfying airflow is reached when 1.1 meters duct is used. This gives a maximum height of 2.8 meters for machinery. The best fit were Sandvik's LH517. In Juno, small LHD are used in the ore passes. This gives an acquired airflow of 6.2 cubic meters per second. To ensure good air quality, a flow of 10 cubic meters per second is used. In Jupiter, a large LHD in the ore passes gives an acquired airflow of 16.1 cubic meters per second. This gives a secondary fan duty point in Juno, where the flow is 10 cubic meters per second and 363.3 Pascal. In Jupiter, the flow is 16.1 cubic meters per second and a pressure of 962 Pascal.